So the problem with the class is that there are a number of people who come sporadically. There's 5 people in this room right now who come almost every single time, maybe 6 people. Then there's 2 people who have hardly come because they're new. Okay, but there's also more people who come sporadically. So essentially, to get an ongoing conversation about something that essentially moves in the same direction every time, as if this is a course, that's insane. There's no way I can do that in this way.
Sure.
So what happens is stuff happens in the class, and it really depends. I often depend upon the people who haven't been here to ask questions like out of the blue, so that everything that I've prepared can be dismissed entirely, and we can start with some other topic, which I therefore can be forgiven for repeating the same topic each week. The topic each week for the last 3 months has been the Big Bang and the Hubble controversy. Okay, the person who started this conversation, because she insisted I tell her something that wasn't the same as everything I had told her previously, isn't here right now. Okay? So she's going to miss the answer to the question that she asked, so I'm going to have to tell it again. So I don't know how to do this sort of thing. So the only thing I can say is we'll make it up as we go along. So I'll tell you things that I didn't know last week, more or less, and that's the thing. That's the reason that I'm really here in the first place, among other things, is to learn things I didn't know, so I can tell you things. The thing that I'm really trying to know, is how big the universe is. That is really my ongoing trying to understand the universe. And you cannot get your head around the universe. It's simply impossible. But if I spend every week here thinking about what it is, how big the universe is, and finally I have some sort of glimmer, and I come in here to try to share that with you, as if you're going to get what I've got, okay? You can't do that. But let me just try something. I'm thinking. Universe is mostly empty space. Okay, that we know. But there's an awful lot of it. I mean, there's really a ridiculous amount of it. Why? And for those of you who don't, who are sort of new, you have to realize that whenever I say the word God, I'm joking. Okay, so there isn't. I'm an atheist, pure and simple. But that doesn't mean that anything I have to say can in any way be used to support my point of view. Okay, you can't prove atheism any more than you can prove the existence of God. I happen to be an atheist, so when I talk about God, it's part of the joke that I'm telling you. Okay, so when God saw fit to invent the universe, one of his really big jokes was that he was going to separate the things that are from the things that aren't by a very large distance. And so the idea, the insanity, that the very nearest star is 4 light years away from us. And that is what the universe considers to be really close. Is insane. The universe is big, but there's nothing nearby. Even the planets are not nearby. I mean, Elon Musk talks about getting to Mars. He's insane. The idea of getting to, I don't think he's insane. I think he's fantastic. But nevertheless, for the purposes of this lecture, he's insane. He's building this starship. He's calling it a starship. It's misnamed by any stretch of the imagination, to get to Mars, and he's got this idea, and he's building this. He's building it. It's so big that it could take 100 passengers between here and Shanghai and land them in 30 minutes. And he says that the price of a ticket will be less than a first class ticket. More than coach, but less than a first class ticket. And this same starship, he's calling it, with the same basic body shape, will be used to bring people to Mars. And the trip to Mars is, depending upon how foolishly you build a rocket, between 3 and 6 months, and 9 months on the way back. People have nothing to do on Mars that we can't ourselves do with robots. But I mean, imagine spending all the money that we're going to spend to get to Mars, okay, but to put people there, okay, who have to get back. Right? So that's a lot of money and capital. But imagine that we spent all that money on building robots that could do the same thing. The robots could wander around, take a look at this, take a look at that, dig here, but instead, we have sent robots to Mars, and they do amazing things, but they're not $100 billion projects. They're $1 billion projects, and half of them fail. Can you imagine? Half of the humans we send to Mars don't get there because they fail. That's not okay. So you have to build, and half the spaceships we have sent to Mars have failed to land, and we're going to send humans there. Half of them are not going to get there? No, so we have to build these things much more robustly. We have to spend a lot of money. But the point is, the Mars is far away, even though it's so close that you can stand on the Earth. And here comes our usual latecomers. We have a few more. I'd have to see, what I've been doing is I've been vamping. I've been avoiding the topic, you see. So it looks like I've been actually discussing what I came to talk about, but I haven't been. I've just been waiting for more people to show up. The spaceships that go to Mars have to be that much more robust to be able to land safely and return people safely to Earth. Okay, I was saying is that there in the 1700s there was somebody who said, I forget the guy's name. Oh, it could have been Cassini, but some of the famous people from the 1700s. One person got together and said, I wonder how big the solar system is. Now, this wasn't the first time the question had been asked. The first time the question had been asked was, let's say 200 BC. But we actually don't know these things because there was a library in Alexandria, which, by the way, there is still a library in Alexandria. A very pretty place. You should go. It's nice. It's pretty. But there was one that in Alexandria 2,000 years ago, and it contained scrolls from or books as they were. Books we call them now, but scrolls then. They contained the entire knowledge of the world. When people came to visit Alexandria, the city of Alexandria would deduct from the manifests of the boats that came, the scrolls that they carried. They would then get copied and then put in the library and then returned. So the knowledge of the entire world was in Alexandria. And then it all burned down, and we have almost no knowledge of what the ancients knew. So when I say to you, they asked this question and got this answer, it could have been the very last person who asked the question and got the answer, rather than the very first person who asked the question. It could have been one of the students. It could have been anyway, the question that was asked by Aristarchus was, how far away is the sun? How far away is the moon? And the thing is, he got answers. This, by the way, is all in the name of explaining how big the universe is, which is, for those of you who just came in, is the question that I'm trying to answer right now. So here's a picture. This, imagine you have nothing going for you whatsoever. No special instruments, no friends, no no friends who happen to have watches, so that you can perform the same measurement at the same time, and which is a good thing to do, because then you can get 2 points of view at the same time, and you can do triangulation. But you don't. You're just one guy, and you want to figure out how far the sun is away. So what you do is, you're on the Earth, and you look at the moon when the moon is half phase. So it's a half moon, okay? And you say, well, if the moon is half lit, then the sun must be here. Why don't I simply look at the sun through, well, they didn't have instruments, so the guy literally looked at the sun, but tried not to blind himself, right? Because that's a very good way of blinding yourself. And because the sun is 5,000 degrees, and if you stare at something that's 5,000 degrees, the cornea, your cornea will start to ignite. You know, to the extent that you fill your cornea with the sun, your eye and your cornea and your retina will begin to achieve the same temperature. So you don't want to be doing that for any length of time. That's why people tell you not to stare at the sun, because you can really burn your eyes permanently. So, of course, he didn't stare at the sun. He did something akin to staring at the sun, but he couldn't literally do that. So, and besides which, the angle that he needs to look at, which essentially is close to 90 degrees, is not 90 degrees. He has to measure an angle that's like 90 degrees, but isn't 90 degrees. And he came up with an angle like 87 degrees, which is totally wrong. Nevertheless, it's good enough to come up with the idea that the sun is 5 million miles away. Because you can figure, first of all, you have to know the distance to the moon. I skipped that step. There's a way to look at the distance for the moon. You can kind of, you see the shadow of the Earth across the moon. It takes 3 hours to cross the moon. You know that the Earth is 8,000 miles in diameter, because you're not Columbus, and you're not driven by misinformation. See, Columbus thought the Earth was smaller, or at least he argued that it was smaller so he could get his money to cross the ocean. He was going for the Indians. If he thought the Earth was 8,000 miles in diameter, he would never have done it, right? Because he would have figured out that the time for him to get to India would have exhausted his supplies. So he imagined an Earth that was so much smaller than the Earth that we have today. But the ancients knew how big the Earth was, because they had taken the trouble to measure it. And the way you measure it is you have a friend, because you need a friend for this one, and your friend is some distance away from you on the Earth, specifically closer to the equator than you are. And you and your friend can, at some point on an agreed upon day, your friend has the sun directly overhead, and so that's where your friend is standing, and you are a few hundred miles away, north of there. When you look up at the same day, the sun isn't directly overhead; it's off to an angle, and how do you do that without using? Without staring at the sun? You build a giant well that's very deep, and if the sun's shadow, the sun illuminates the bottom of the well, then it's overhead, and if it's not illuminating the bottom of the well, then it's off to an angle. So using the well technique, they were able to this guy saw the sun directly overhead, this guy didn't. They measured the angle, and they figured out how far away, how big the Earth was at that time. They got an angle of 5 degrees, and they figured 5 degrees, they walked the distance, it's so many cubits, stadia, whatever, and they figured out, the Earth is approximately 8,000 miles in diameter. They knew that years ago. So Aristarchus knew the diameter of the Earth, and then he could see the Earth's shadow on the moon, and he could figure out more or less how far away the moon was, and he got that pretty well. He got that right within a few tens of percents. He got very good. He got a very good number. But getting the distance to the sun, that's really much harder. But he got 5 million miles. He got 5 million miles. As you know, the sun is 53 million miles away. 93 million miles away. So, but think about that. Now he knows the sun is 5 million miles away. And then he makes us a simple little assumption. He says, you know those things up in the sky, those things we call stars? They're suns. I believe they're suns. But they're dimmer. So if they're dimmer, and all stars are the same, then how far away are those stars? And he gets it. He gets the universe is big. He gets it. He gets light years. He doesn't have the word light years, but he certainly gets that things are light years away. He gets the universe is big, and certainly not flying around the Earth. So we knew all this a long time ago, but it didn't make a difference because the Christians got involved and decided that Aristotle had the last word for about 2,000 years. Aristotle, as you probably know, was a guy who had the point of view that you could figure things out without doing any experiments. So everything he did was based on logic. And one of his more famous logical flaws was things that are in motion have to be kept in motion by continuously pushing them. Otherwise, they stop. And that is called Aristotle. Well, an arrow flying through the air needs to have air rushing in behind it to keep pushing it forward. Otherwise, it would simply stop. He didn't know anything about friction. And it wasn't until Newton that we had Newton's law of motion, which says an object of motion stays in motion unless acted upon by an external force. And if you knew that one, you could have figured out that the moon was gravitationally sucked up, being moved around the Earth by gravity. So all you needed was Aristotle to be wrong for somebody to figure out that there was gravity. But anyway, off the topic. So with this diagram, they get that the stars are far away, and that doesn't. But those are not the right answers. That's just an answer letting you know that there's something. Around 1700, there was a guy, I don't know his name, who figured out that figured out how far away Mars is. He figured out how far away Mars is. And the way he did that is he had two people on the Earth looking at Mars at the same time. This guy here, this guy there. And Mars, while far away, and if you have a telescope, which is capable not just of looking over there, but looking right over there, and measuring the angle exactly to a much greater precision, you can see that if you move your telescope from this side of the Earth to that side of the Earth, that Mars moves in the sky with respect to the background stars. And so this person was able to measure the distance to Mars. So they began to get it, how big the solar system really is. They knew already, but they now started getting the good numbers. And the good numbers got much better when we invented telescopes. And the best one we used was, we had a telescope that literally went zap, and could zap the moon, and could zap Venus. So that we knew the distances to all these things. So normally at this point I don't ask for questions, but since there is now a greater degree of people sleeping than normal, I'm going to ask for questions. I don't normally invite questions at this point. Are there any questions? Okay, no questions. But you can have questions. The point is, you can ask questions and raise your hand at any time, right? Okay. So let's see.
I just was wondering, when he zapped Mars, how did he know do you know when it came back? Was there a meter involved?
We see. I use the word zap, which was designed to incur a question.
Ah, it worked. Okay.
How do they know? Was there a mirror involved?
Yes, I mean, how did you know?
Right.
What was the interaction?
Well, what they did is, around 1947, somebody noticed that their radio receiver was getting a lot of noise, and at some point they decided to point it at something. When they pointed it at Jupiter, they realized that Jupiter was noisy, and they had no idea that the outer space had any noise associated with it, radio noise that you can hear. And so they started designing these dishes that could point at things, and parabolic dishes that could point at things and listen to the noise coming from there, and then point it, and then they could listen to the noise coming from there. No Jupiter, noisy Jupiter. No Jupiter, noisy Jupiter. And suddenly the idea of radio astronomy came to be. Those same dishes, listening can be used to send signals. So that's called radar. So a radar pulse was sent to the moon, and it bounced off of the moon and came back. And you can time that very well, and you can get the distance to the moon very easily. And they even did that with Venus. They measured the distance to Venus, and they got a radio signal back from Venus. I just think that's amazing that you could do that. And they did that, I guess 50 years ago. Yes?
How far out can they go with, radio measuring? Measuring with
The measurement, you can measure only a short distance. Venus, I think they've gone as far as Jupiter, which, is a short distance. It's only 5 light hours away. So you send a pulse out, 10 hours later you get something back, you go, aha. But I think as far as Jupiter is about as far as you can get. I think the interesting thing is if you weren't waiting, if the response you were waiting for was not the echo, but someone saying, I hear you, some intelligent life, okay? How far away could you send a radar signal packed with all sorts of interesting information like pictures of us, and how far away could aliens get that signal and respond? And the answer is not that far. It is pretty far. Let's say 100 light years, maybe even 1,000, depends upon how good the technology is of the people or the aliens or reptiles receiving the signal. But nevertheless, considering that the universe is vast and nearby is essentially not vast, let's say there's 1,000 planets between here and the nearest radar signal that can be heard by intelligent aliens. You need more than 1,000 planets to have the chance of having developed life. We'll talk about that some other time. But generally, we're not going to get a signal from an alien. We can just bounce the things off the nearby things, and that's just Jupiter. Bouncing off nearby things. But the universe is very big, and how big is that? Well, here's a picture of the universe. Let's see if that works. There you go. There's a picture of the universe, and the thing about this picture of the universe. Let me see if I can do this better. Yeah, this is better. This is a picture of the universe, and the places I'm talking about are here. Look, this is not some mucked up child's drawing of the solar system, this is an actual picture of the solar system which uses one piece of data to arrange the data. They're using logarithms. So if something is a distance of 1 away, which is what the moon is. Where's the moon? There's the moon. This is a distance of 1. Okay? Jupiter is at a distance of 5. 5. That's 10 to the 5th further away than the moon is. So that's log 5. I mean, not log 5, but 10 to the 5th further. You see, and Saturn is like 10 to the 10th, well, maybe 10 to the 6th further away. So all of this is nearby, and the rest of this picture, which this is an accurate picture of the universe. You go from 10 to the 5th, 10 to the 6th, 10 to the 7th, 10 to the 8th, 10 to the 9th, and very quickly you get to stars and galaxies and clusters of galaxies and the end of the universe. So the entire universe is in this picture, but not as a child's picture. This is an accurate picture of the universe. But what we have been talking about in this class, if you had been here, and there are a few people who have been here forever, you know that we have spent maybe 2 years talking about this part, the solar system. And now I've been skipping the conversation about the things that we call, oops, I'm going to fix the camera for a second. We have skipped in this class a small amount of things like the galaxies, we skipped the stars, we skipped the galaxies, we've skipped these clusters of galaxies and the large-scale structure of the universe, and we're really literally almost at the end of this picture, the end of the universe. We're talking about the Big Bang. So, if you will, in this class, there's lots of stuff to talk about that we skipped. The reason I've skipped it is because you can see it only occupies a small part of the picture. This stuff is so far away that we don't have as good a story as the story of the planets. We visited all of those. So, although I'll get to the galaxies, I'm really interested in talking about the universe. How did it start? How did it get created? And one of the things that happened this week for me is I figured out a way for me to be happy about the creation of the universe. Okay, so if you will, you can now share in my joy over how I can be satisfied without having there be a God, how the universe could have been created. Okay, it's not, of course it does involve another belief system, which you have to trade for the previous belief system that you might have had. So the first belief system you need is, it's not strictly necessary, but I think it's really important to the thing. You need to believe in infinity. You need to believe that the universe is infinite. Now, it isn't actually strictly necessary for everybody's there's lots of arguments in all sorts of ways and all sorts of controversies about this. And I'm not saying that this is fact. I'm saying this is a theory, which, by the way, is probably, and not probably, completely unverifiable. But it does have a neat sort of story to it. So imagine that the universe is infinite. That means also that it has been infinite in time, forever, and in space. Now you can just go home with that and try that on for size. Okay, you don't need the rest of this lecture. Okay, it's because that is a reasonably mind-expanding sort of thing to try to do. I mean, to my mind, it's a lot more reasonable than a creation, because you don't need a first cause. You don't need a creator. And the Big Bang, no matter how you slice it, somehow is a creation. So, and yet the Big Bang is true, but we need to understand the Big Bang in, hold on, I'm going to turn the camera towards me. We want to understand the Big Bang in terms of, but not in terms of a creation. So, infinite universe, infinite time, there was a Big Bang. How do we put that all together? Well, the first thing that I learned this week that I've always known, and I'm going to wake up one of our classmates because she's always interested in this, so I'm going to, hi, just waking you up, okay? Because I know you like this stuff.
I did when I came from work.
Right.
I came uptown.
Right, I know. So I know that, and by the way, anybody who falls asleep in this class, I assume it's not my fault.
No.
And I assume it's not your fault. I just assume you didn't get enough sleep. That's all. And
Walking around too much.
yeah, and just as a matter of course, I just want to say that I slept through every single one of the classes that I ever took in my life because I didn't get enough sleep. So I don't know about you, but I was very busy. In my case, I was busy watching television. But my parents didn't know there was a crack in the door and I could watch television. I could watch the Late Late Show, So the thing that came to me this week that made a big difference is I realized that the Big Bang was not an explosion. How many of you, up to the moment that I've said this, have always thought that the Big Bang is an explosion? Okay. Right.
Not an explosion, but what you're saying has an obvious problem. What you're saying is that time existed. Time supposedly was created at the moment, instant of the Big Bang.
Right.
You're saying that time existed previously.
Yes, I am saying that time existed prior to the Big
Well,
Bang.
that supposition I find very...
Okay, well, first of all, I have always said, Howard, I've always said in this class that time was created at the instant of the Big Bang. I've always said that. And frankly, I don't have enough expertise to say that that's not so. Okay, maybe time is, and in fact the stuff I read this week did not address that particular point. So it still may be reasonable to say that time was created at the instant of the Big Bang and still continue on with this lecture without pause. But for the purposes of what I understand, I'm going to say, no, I no longer need that as a thing. Because the Big Bang, the first thing I learned this week was that people who study the Big Bang do not believe that it was an explosion. And they do not believe, and this is the thing that I really didn't know, it began with a singularity. Now, a singularity, here's the thing about a singularity. A singularity is when things go bonkers and go to infinity, or start at zero, whatever way you want to think about it. Let's think about zero, okay? You have 0 coins in your pocket. Now you have twice as many. Now you have 4 times as many. Now you have 1,000,000 times as many. How many do you have?
0.
0. So, if the Big Bang began at t equals 0, and then a few, then 10 to the 10 times later, this was true, and then 10 to the 20 times later, that was true. It's still at 0. So let's not use 0. Let's just do when scientists talk about the Big Bang, they never talk about 0. They end up having to talk about it because somebody wants to know when the Big Bang started, so somebody says 0 and that's good enough for them. But the fact is that multiples of that don't work. We don't talk about it that way. We talk about it from now backwards. So we talk about, this is 13.8 billion years since the Big Bang. That's a good number. 10 years ago, it was a slightly different number. 20, 30 years ago, we have a number now, 13.8 billion years. That's a number, okay? That number doesn't look like it's going to change anytime soon. Divide it by 10, and it's 1.38 billion years ago, okay? And you can see 1.38 billion years ago. You take out your trusty telescope, you look, and you see a galaxy that is so far away that the light has taken 1.38 billion years to reach us, and that galaxy is that old.
At
No.
least that.
No, I actually said that wrong. That galaxy is 90% of 13.8. We need to, in order to see 1.38. See here. See this galaxy? This is close compared to the numbers I'm talking about. I'm talking about here. Okay, that is 1.38 billion years since the creation of the universe, which was here. So we're talking about 1/10, 100th, 1,000th, 100,000th, 10 to the 10th less each time, 10 times less each time, and we keep looking at those numbers back in time. Here's what that looks like. Here is a chart in which the numbers are divided by tens. So this is 1 million years. This is 1,000. This is 1 million years after the Big Bang. This is 1,000 years after the Big Bang. This is 1 year after the Big Bang. This is 1 hour after the Big Bang. This is 1 second after the Big Bang. 1 millisecond, 1 microsecond, 1 nanosecond, and so on. Look at the distance we have to go. Look at all the divisions in time. There is no zero on this chart. There is no zero. You can't make a zero in here. You can't keep dividing it until you get to zero. So this is the Big Bang. There is no zero. Howard, there is no zero on this chart. That's the thing. I have been telling you, and you have been reading, and I've been reading, oh, and then there's zero. But you can't get to zero from here. You can't. So what happens if you don't need to get to zero from here? What happens if you can draw a line right about here and say, starting here, something else was going on? What happens if all of this stuff, which can be true, is speculative? And what happens if this pink area here has been somewhat proved? This is all good physics. This piece here has been awarded a Nobel Prize. So people believe in that little pink piece there. Okay. The yellow pieces below this we really don't have any proof for. This has some support. And what is the pink piece? The pink piece says that the universe, which, if you will, was infinite, in one region of the infinite universe, which was kind of stuffed to the gills with energy, but not matter, you had energy. And the energy was sitting there minding its own business for who knows how long, okay? And then, at some point, the energy, I don't know, woke up, decided to do something, got angry, and decided to inflate the universe. And that period of time is called inflation, and it takes place just within a few pieces of from 10 to the minus 33 seconds is when it began, and maybe 10 to the minus 34, 35 seconds is when it ended. The universe grew from what you could, let's say, a walnut, to the observable universe in 10 to the minus 33 seconds. There's no reason that you can't build a universe instantly by what you're doing is you're expanding space. And when Einstein said you can't travel faster than light, he didn't raise his hand too high to say, well, but by the way, you can't travel, but space can travel faster than light. Actually, of course, Einstein knew very quickly the space can travel faster than light, and it does. It's just that light can't. Yes, Howard.
What if the energy you're talking about is another name for zero?
What do you mean?
That what we call zero is this massive amount of energy that you're describing. If we make that a massive amount of energy and we call it zero, then we have a zero.
Well, no, but you can't call something zero. Oh, yeah, you can arbitrarily assign zero to something, but the number actually
But the
would
number
be.
is just a number we made up. But if we call it, we made up all the numbers, but if we call that energy zero, if we decide to, then we have a zero. And I would call it zero. You wouldn't.
Okay, no. I don't see any reason to argue about it, because the name of it isn't important. So, if you don't mind, I'll call it George. Yes.
And I know you don't like Kabbalah, but in Kabbalah there's a thing called tzimtzum, which is that an instantaneous, not an explosion, but an instantaneous glint appeared and then the universe appeared. And that's tzimtzum, that out of the nothingness there was something. And that's tzimtzum 3.8
Right.
billion years ago.
Again, creation. What I'm trying to get away from here is creation. Okay, the idea of
I didn't say God.
No, you didn't. I'm just saying first cause or beginning. Okay, I'm trying to get away with the beginning. Okay, because the first thing I said, and actually I think you were asleep at that moment, was that I want you to believe in infinity, and I want you to believe in infinite time, both forward and backwards, and I want you to start there, as the conversation start there. So if you start with, time has always existed, except for the fact that we have an argument that it started at the Big Bang. But try to imagine an infinite amount of time, and try to imagine that at some point in this infinite universe, some little part of it had enough of being just this and decided to pop like popcorn and inflate and become the universe. The fact is, there's no reason to not expect that right next to it, in this infinite universe, there wasn't another piece of popcorn which also inflated. Not at the same time. It could be doing so now. We would have no knowledge of it because we can only see so far in the universe. We cannot see beyond a certain distance. When I was showing you the observable universe, that's the observable universe. That's not the universe. That's as much as we can see. So if there's another piece of popcorn going off somewhere else, and it's happening just now, we couldn't see it. And we never would be able to see it, because the light from it can never reach us in ever. Not like, well, if we wait a little longer, it will reach us. Problem is, this space is expanding, so that any light that's coming from the outside here and wants to get in to inform us will never get there, because this space is expanding so fast that this light can never reach us. So there's a limit to what we can know. And if I say that out here there's all sorts of popcorn going on, you can argue with me, right or left. I can't prove what I'm saying any more than you can prove what you're saying. But the idea the idea behind it all is that we're not special. That the universe is not made for us, and therefore there's no reason to believe that there aren't other universes, and you now you have the word multiverse. So in the multiverses out there, the infinite number, I mean, if you have another one, and I've postulated infinity, then there's no reason to not believe that there's not an infinite number of them, having been going on for an infinite time in the past, and will go on for an infinite time in the future. Now, this is science. It's actually, it's because the part that is science is this thing called inflation. About 40 years ago, there was this guy, Guth, his name was Guth, and he came up with the idea of inflation. And since then, inflation has become almost a dogma, despite the fact that it has certain things that have not been proved. It made 6 predictions. 6. It made 6 predictions, 5 of which have been verified. So, and the 6th, the poor guys standing at the North Pole, freezing their tushies off, are working on the 6th one, and they a couple years ago, they raised their hand and said, "We found it, we found it." And the rest of the scientists took a good long look, because surely they worked very hard on the deal, and they turned around and said, "You didn't find it. Try harder, build something bigger, more expensive. Keep your looking at it on the South Pole. Keep looking. It could be there, but you need a better, bigger instrument to find it." And they're doing it. They're looking for it. That'll be the 6th proof of inflation. So, yes?
Could one look up what are the 5 proofs of inflation and find it on Google, or is it something that is without confirmation?
No, of course, but don't Google 5 proofs of inflation. What you do is you just Google inflation. So inflation.
But we'll get a bunch of money, financial material.
So inflation, cosmology. Okay. So overview. Let's see, theory. So math. Duration, reheating, motivations, horizon problem, flatness problem, magnetic monopole problem, for example. Magnetic monopole. Magnets. They have a north and a south. And if you break the magnet in half, they have 2 magnets with a north and a south. There is no magnetic monopoles. There are always dipoles. On the other hand, you can take a sphere, charge it with electrons, and then get close to it, and your hair stands on end. That sphere is full of electrons more than there are protons. Electrons are singular. There's an electron, there's a proton. They're not the same. You can separate them. They don't turn back into one another. It's an electron by itself, a proton by itself. There's no north and south. But there should be, according to what we think. But there isn't any. So we think harder, and we say, why isn't there any magnetic monopoles? It turns out that you could make magnetic monopoles, according to what we know of the laws of physics, if the universe ever got hot enough. So if the Big Bang was hotter than it was known, see, inflation cooled it off. If the Big Bang got hot enough, it could have created magnetic monopoles. It didn't get hot enough. It's one of the proofs that inflation cooled off the universe before monopoles could be created. So that is one of the predictions of inflation. An explanation for why there aren't something. Of course, you could say that's an explanation for a theoretical particle, and this is a theoretical reason why a theoretical particle doesn't exist. You could object. Okay, you could object. But if you are deep in the math, you wouldn't. I assume. I'm not deep in the math. So then there's various models. Early inflationary models, the idea of something called slow roll inflation. The idea of slow roll inflation means that the inflation happens here. Starts off slow, then whoop, it happens, and then it stops. And then over here, it happens again, and it stops. So that's that. There's a thing. See, there's a problem in the universe that really needs to be explained, and that one is this. Hold on, that one is. Yeah. This is the universe. It's a birth picture of the universe. It was taken, yesterday, by a very expensive satellite that they launched a few years ago. What I mean yesterday, I mean in astronomical time frame. It happened recently. This is a picture of the universe as it looked when 308. They actually have a number on this. It changes slightly. 380,000 years after the Big Bang. 380,000 years after the Big Bang, the universe looked like this. What does this mean? Well, first of all, the red means hot, and the blue means cold. And this projection, as you know, would be flattened into a sphere. So this is how you flatten a sphere into a projection of some sort. The difference between the blue and the red is 1 part in 30,000. 1 part in 30,000. In other words, the universe is the same temperature everywhere, but if you look really, really carefully with expensive instruments, you can measure differences in 1 part in 30,000. And the temperature of all of this is 3 degrees above absolute zero, because when the universe was very hot once, it got very cold. When it expanded, it started hot, it got cold as it expanded. The universe is now 3 degrees above absolute zero everywhere. But the noise from the explosion is everywhere, and everywhere you look, there's the universe like this, because the light is still coming at us. Why? Because there's no place that the universe was created. There's no center of the universe. There's no. In fact, if you look to find the center of the universe, and let's look, see, okay, where is the center of the universe? I'm going to look very carefully, and I look in this direction. Everything is speeding away from me over there, and then everything's speeding away from me over there, and then everything's speeding away from me over there, and yeah, everything's speeding. I'm the center of the universe, clearly.
Sherlock Holmes.
So clearly you got that wrong, and if you asked anybody else in the universe, they would come up with the same answer, that it's speeding away from them. So the other side of that conversation is there is no center of the universe. Okay, so this is the universe, and anybody would see the same picture of the universe. The problem with this is the universe is at the same temperature. The problem is, plus or minus 1 part in 30,000. The universe is at the same temperature. Well, that's fine for the universe, but explain how this guy and this guy agreed on the same temperature, since they could never have had any time together to agree on the same temperature. The temperature on that side of the room over there is a little colder or warmer than over here, because the air from the vent here hasn't reached the thermostat there yet. For the thermostat, the temperature is different in different parts of this room, probably by measurable degrees, not millionths of degrees, because you have to reach an equilibrium for it all to come together and decide to be the same temperature. And if you haven't met, then you can be different until you meet and agree. What this says is the universe met. It had a conference, it decided on the temperature, and then after the conference on what temperature which should all be, they separated. The separation was what inflation did. Inflation said, now that you've agreed on the temperature, let's separate you rapidly and make the universe in a split second. And literally, I mean 110 to the minus 33 of a second, they separated the universe into these pieces. But the fluctuations in the temperature that were true at the time were preserved. These fluctuations can be predicted by quantum mechanics. And although we have the universe here as big as the universe, quantum mechanics, which is the smallest thing going, can speak to the fluctuations and say, let me take a whack at it and see if I can get a prediction on what these fluctuations statistically, not this will be red and this will be blue, but how many big blue patches, how many big red patches, how many small blue patches, how many small red patches. That's the statistics. Let me predict that. And inflation predicts this. If inflation predicts this incredibly well. So the universe is well established to have had a period of inflation. That's yes.
This may sound stupid.
It couldn't sound any stupider than this, really.
Your blue is cold.
Yeah.
So is that a presumption after an explosion, then things are going to get, after they've exploded, they're going to get cold?
No,
Okay.
it couldn't be a better question. Couldn't be a better question.
Okay.
Okay. Your question indicates that I managed to confuse myself and you at the same time.
Not hard to confuse.
No. Really, you've done it. That's see. I have to say, I put this class on the web, okay, and I have like more than 25 episodes, and the thing that I think makes this class unique, that doesn't exist in any other class, is questions like that. Is you don't get in a normal class. If you had gone home and read the book and asked that question, I would have told you that you didn't read the book. But since I am the book and I poorly explained it, then I get to really try to answer that question. And I don't think any other classroom situation on the web has the context of asking really good questions. So what is it that you asked? You asked if actually, could you ask it again? If you could.
I was trying to make the assumption that, well, the presumption that the blue is cold.
Right.
So, is that after an explosion, prior to an explosion? In other words, is the blue eventually going to get hot? Is the heat eventually going to diminish? And then, I didn't ask this. Then instead of inflation, would you have deflation?
Okay. So the deflation part, I can answer no. No deflation. Okay. But what I clearly neglected to mention, and this is a property of the fact that in this class there are at least two categories of people. There are the people who haven't been here before. There are and Shirley would know the people who have been here before and already know, the people who have been here before and forgot what I said last time, the people who have been here before and didn't understand it the last time I said it, and so they're asking it for the first time. I think you fall into the fourth category. I've said it before, and I don't think you understood, unless you were one of the people who didn't hear it when I said it the first time, or the second. I've said this in this class, and if you go to the video, I think we'll say maybe 5 times. Okay. Nevertheless, I do believe that I never explained it well enough, even every time, which means I may not be able to do it this time either.
Sorry.
Yes.
When I first looked at it, it occurred to me immediately that it was land versus water.
Right.
That may be off the...
Right. That's off the chart. Yes. But it isn't.
It's not land
It's not.
and
It's
water.
not land. It's not continents. Although what you are seeing is something called, I think, the Mercator projection, or
Yes, yes.
yeah, and so your mind is going to, oh, this can be mapped onto a globe, and the globe would have land masses and water masses. So your brain is trying to make land masses and water masses out of this. But the only part you should take from this can be mapped onto a globe, and the globe is the globe we sit inside of, and we're looking out. This is the outside of the globe, but we're seeing it from the inside, okay? But this is from the outside of that globe, and so what that globe would look like if mapped on and looked from the outside. But it has obviously nothing to do with water and nothing to do with land, and really the magic here is really amazing, because what these things are called is quantum fluctuations. And quantum fluctuations is where the universe has reserved the right to be magical. The universe has created a law of nature, and in that law of nature, one of the first laws of nature is there are certain things you will never know because you're not allowed to know them, because there's nothing to be known. Let's use God. God, have decided that there's just so much you can see and no more. Now, what is that curtain? The curtain is a smallness, a certain degree of smallness. If you make a really, really small piece of space, and this is in the neighborhood of 10 to the minus 35. I won't say what the units are, but that's a small number by itself. 10 to the minus 35. There's a certain length. It's got a guy's name associated. It's called a Planck Length. If you look at things that are smaller than 10 to the minus 35 and try to see what's going on inside there, you're not allowed to know. Because nobody knows. It's called, and the word for it is the things that are going on inside there are called quantum fluctuations. So anything can happen. And if you use a small amount of time at the same time, if you look for a very brief amount of time, you might see what's happening outside of that. So what I always say is this: the laws of the universe allow for, in a very small cube that is the size of a Planck length, the laws of the universe allow for clowns to pop in and out of existence for a split second, to wave their hands and then pop back in, all within a quantum time frame and a quantum length. And that's okay because clowns in that small space are permitted by the laws of physics, meaning anything goes, we don't know, including clowns. So inside of that cube, there are things that go left that are hot and cold because they decide to go in different directions. And if you take the fluctuation and suddenly you inflate it, then this is hotter and this is colder forever. So this is a forever picture. It doesn't get any different than this. This is a snapshot taken by inflation that took what was true in a teeny little space and expanded it. So this is the fluctuations that can be true in that space we never could see inside of. But now we're seeing inside of it. We're seeing inside of it. We saw the fluctuations inside of it. They've been expanded to the size of the universe. And now we say, well, gee, inside of that cube, what does quantum mechanics say about the fluctuations? These are exactly the same temperature, but there's a slight difference because they had this fluctuation. This clown didn't have enough time to reunite with this clown. These two clowns, which were wearing white face and black face, got separated before they could ever get back together again. And that's why we can see the difference, and we can predict the fluctuations. And these are measurable. Does that answer your idea of it, or you're still not? You're still seeing it as ocean land masses?
No, I definitely threw that away, but now I'm inside that form and pushing around occasionally.
Right.
I don't know what that means.
Kurt.
How could this picture look without inflation?
It couldn't be. It couldn't exist, right? Because the inflation is what gave us the universe in the first place. Because the universe wouldn't have been created without the fact that something the size, let's say, of a soccer ball became the size of the observable universe in some 10 to the minus whatever second.
But so radiation would still be there even if nothing was created.
Say that
So
again.
Radiation was already there, yeah.
Radiation was there.
So it would still be there. We just wouldn't have galaxies and stuff. So
Right.
if you theoretically could make a picture, would it just be uniform, or yellow, or in between?
Let's imagine a place let's imagine there's a place with no cosmic inflation. It's next door, but it has decided to become a universe next week, not now. So it's right next door. It's going to inflate, but it hasn't. So inside of there are these.
But it's not radiation is in both cases. It's only the inflation that's different.
Right.
So if somebody inflated this enormous speed as it does now, what would the picture look like? If one could take it, what
Well, you have to take a small region of space, which has a large amount of energy, and inflate it very quickly. But I can't imagine how to create the universe you're talking. You're talking about a universe that's differently created, right?
No, everything's the same except no fast inflation, just a constant, Hubble constant from the beginning to now.
Well, the problem with the Hubble constant being without inflation is that they couldn't invent the universe without inflation. There were 5 problems with the universe that didn't make sense until Guth invented inflation, and then those problems. So you'd have a universe filled with magnetic monopoles. Okay, if there was no inflation, and magnetic monopoles could have wreaked havoc on the universe. I don't know. I don't know what it would be like to have a magnetic monopole in my pocket, but I have a feeling it wouldn't be happy in my pocket. I wouldn't get a magnet, get the whole set, get the north and the south. I mean, if you could get the north and the south, they would destruct each other and they blow each other up. I mean, I don't know how dangerous magnetic monopoles are. They're probably not good. And also, the universe has only matter, not antimatter. What happens if there was a point at which they didn't annihilate each other? Then they'd be busy annihilating each other right today. My chair would eat the next chair because it was made of antimatter. I have no idea how bad the universe would be without inflation. It's a great question. I think superior minds should be asked that question, because it could literally torture a good person who knows what they're talking about, right? Well, okay. So I think I should stop now.